this module, we are going to continue our discussion of strengthening metals. And for the second part, we're going to talk about what's known as precipitation hardening or precipitation strengthening. Okay, so precipitation strengthening is a common technique used with aluminum alloys. So if you're thinking of, for example, a lot of commercial airplanes up to this point where they've started to transition to carbon fiber, but before that there was a lot of aluminum based alloys used in planes like the Boeing 767, and this is a good example of a precipitation strengthened aluminum alloy. And so if we look at the structure of it, and so this is taken on a microscope, optical. You can kind of see the length scale we're looking at. And you'll notice that there's kind of a uniform lighter gray color, but then there's all of these small little dark particles. And these are the precipitates. So they precipitate a solid from a main alloy phase, and that those particles, those precipitates, give it strength. And we're going to talk about how that happens. All right, so this is kind of a schematic of showing us how these particles, these precipitates in an aluminum alloy or carbon, or in iron as well, can strengthen it. So the first thing to note is that these precipitates tend to be ceramics, or they tend to be hard precipitates. So for example, it might be silicon carbide, that's in iron, or it could be an aluminum particle made with the alloying elements. And for the most part, these precipitates are harder than the other phase, the main phase of the material. And so there's basically two ways, if a dislocation is moving through that material, how this precipitate can kind of impede or slow down its motion. Because again, that's how we strengthen a metal, is plastic deformation occurs by slip or movement of dislocations. And so if we can slow down that movement or make it harder to move, then we're strengthening the material. So the first way is if we think about a dislocation in what we call the matrix, so the main phase of the material. So it's here. This is an edge dislocation, and it wants to move to the right. And so it's initially moving in, say, the aluminum phase, but then it reaches a precipitate here in the middle. Or same thing, we can have the main phase, and we can have a series of precipitates here. But the main idea is that the first mode is that edge dislocation moves, and once it reaches that precipitate, it either has to go around it or through it, right? So those are the only two options. And so this first method is looking at shearing that particle. So if it shears that precipitate, it's a harder material, and so it's going to take more shear stress to move it and to shear through this particle. And so we have to add more force to shear this particle because it's harder. So that's the first method. So we can actually kind of go through the precipitate. Here, this is a top view. This was the side view showing the edge dislocation. This is a top view showing the line of dislocation. So the green line here is the dislocation line. And so initially it moves through this, again, matrix material fairly uniformly and with a constant force. But once it reaches the precipitates, if it can't shear those precipitates, what happens is it kind of bends around these precipitates, and you see it kind of bow, right? Because it's being blocked here. So this dislocation wants to advance, but it's getting what we call pinned to these sites. And so eventually what can happen is it can move completely around the precipitate and then basically kind of pinch off the dislocation, but it does require more energy, right? It takes more energy to bend it around this dislocation. The dislocation to bend around this precipitate. So again, to advance that around the precipitate, it requires more energy, more force, more shear stress. And so the more we have, the more spacing between these or sorry, the more particles we have and the less spacing between these means that the yield strength is going to go up, and it's going to go up by 1 over the spacing. And so that kind of tells us what gives us the most hardening or strengthening. So we can get a maximum strength by having very small, well dispersed precipitates, so that spacing is really small and uniform. So here, these are very small particles, and so there's a lot of these small particles, and so we'd have to shear a lot of these, or we'd have to move around them, and that requires more stress. Here, if these particles become really large, then the distance between them goes up, and therefore the strength goes down, because it's a reciprocal relationship. So we really want smaller precipitates and more of them if we can help it. That gives us the maximum strengthening. So this is all, another method for strengthening metals. And what I'll say is that this isn't actually in the chapter 8 about strengthening. This is actually in chapter 11, because the formation of these precipitates is something that we haven't talked about yet. This is actually going to come back when we talk about phase diagrams in chapter 10 and 11. So we'll come back and talk about how these precipitates form later in the class.